Good afternoon. I am Shakti Venkatesh from the Department of Physics, KLE College, Rajajinagar, Bangalore. So in today's video, we are going to see conversion of galvanometer into voltmeter and meter. So first we will see conversion of galvanometer into voltmeter. So first our circuital arrangement is here. So here we are going to have our circuit. So the circuit has, so this is our circuit. So a circuit is going to have our battery, key, this is a rheostat, so this is a galvanometer, this is a variable resistance box, and this is our voltmeter. So here if you could see, the rheostat has got two lower terminals and one top terminal. So the top terminal is given by an upward arrowhead, like this is the top terminal. So here this is our battery, and so this is our rheostat and our galvanometer and resistance box and voltmeter. So as it is given in the circuit, we have arranged all our apparatus. So these apparatus are being arranged, and now the circuit connection has been done. So the circuit connection first, from battery's positive we have a wire that is to be connected to the lower end of the rheostat, and from the same point we will have to take one more wire and connect it to our galvanometer. So this is positive of the battery, one wire, this red wire, see, we have connected it to the lower terminal of our rheostat, and from the same point we have taken one wire and given it to our galvanometer. Now if you could see, from the same point where there is a connection, we are taking a wire and connecting it to voltmeter's positive. See, we have connected it to galvanometer, I said no. So from the same point, this black wire is going to come to our voltmeter's positive. So one half of the circuit is done. So the other half of the circuit, if you are going to see, here voltmeter's negative is going to be connected to my variable resistance box. So voltmeter's negative is over here, the black one is negative. So it is connected to my resistance box, variable resistance box, and from the same point where voltmeter's negative is going to the resistance box, we have to take a wire and give it to the top terminal of our rheostat. So this is my connection. So that is means that is connected to the voltmeter's negative. So here you can see that. So that itself, again there, the same point, there is one more wire taken to the top terminal of the rheostat. So there it is going. So now again battery's negative is connected to the lower end of the rheostat. So this is battery's negative, so this green one is negative, so that is being connected to the other lower end of my rheostat. So you can see that the resistance here is a variable resistance. So here you can see it has got so many values. So these values are nothing but the resistance value, that is desired value, can be got by unplugging the resistances, that is the desirable resistance, whichever we need we can unplug and use. So now this is our galvanometer. So this is how a galvanometer looks like. So all the values of this galvanometer is being written behind it. So the resistance of the galvanometer, the figure of merit value, R value and resistivity, everything is written behind the galvanometer. So I am using this. So if you see the galvanometer here, so here it's 0 on either sides of the galvanometer, there are 30 divisions. Okay. So this is my voltmeter. So the range of the voltmeter here is going to be 1 volt. So here it has been divided as 0.2, 0.4, 0.6, 0.8 and 1 volts respectively. So it is going to be the range of my voltmeter is 1 volt. Okay, so now as per the circuital arrangement, we have connected the circuit, and now what we are going to do is we are going to theoretically first calculate our R value and check if experimentally also we are getting the same R value. Okay, so first let's theoretically calculate the R value. So theoretically, if you could see, the observation has got galvanometer resistance. As I said, these are given behind the galvanometer only. Figure of merit also is provided for that particular device, whatever is the G and K value I have written. So number of divisions on either sides of the 0 of galvanometer is 30, we just saw it, and current that is required for producing full scale deflection we have to calculate. So the formula for it is Ig equal to N into K. N we know it is number of divisions, and K value was provided 20.4 into 10 power minus 6. So my Ig value here is 612 into 10 power minus 6 ampere. So next is range of my voltmeter is 1 volt, and the value of resistance to be calculated. So this is the resistance that I am calculating mathematically. I am going to calculate and check it with my experimental R value. So theoretically R equal to V by Ig minus G. So V is 1 volt, Ig value I found already equal to N into K minus G value. G value is 98, it is given already, so that I am going to substitute it off and I got the answer. So final R value what I am getting here is, that is very important, R value is found to be 1535.16 ohm, that is 1535.16 ohm is my theoretical R value. Okay, so experimentally also the same resistance if I am getting or not, I will see. So let me check it. This is my first trial. When I did, I got 1515. So now let me check if I am getting a nearby value or not. So first what we are supposed to do is we have to start unplugging the resistance. So my circuit is being switched on. You can see the power is switched on. So the battery, the resistance box over here, I can unplug the resistance, say 1500. I am unplugging my resistances. So I am checking for the deflection. So not exactly, I am not getting, I have to get 1 volt here and the deflection should be 30. So it is not 1 volt yet. So I can use my rheostat and I can move it front or back like this, so to make the fine adjustments. So still I am not getting. I can unplug the small resistances, let's say start from 10 or 20. So 10 or 20 I am unplugging. So I can, after unplugging, I have to adjust my rheostat. So when I am adjusting my rheostat, I am getting my deflection over. Okay, here my voltmeter reading has come to almost, yeah, it has come to, you can see that it has come to 1 volt and the corresponding G value if you are going to see, so the deflection has come exactly to 30. So at this point I have to calculate what is the resistance that I have unplugged for getting this value, the value to be, the deflection to be 1 volt and 30 in my galvanometer. So the values are 1500 and so here a 20 and a 10. So it is 1530, 20 plus 10. So for my experimental value to be 1530 ohm, I am getting my voltmeter deflection to be 1 volt and my galvanometer to be 30. So my experimental and my theoretical value, when I am going to compare, they are almost the same. So I have successfully converted my voltmeter, galvanometer into voltmeter. Similarly, we can convert our galvanometer into ammeter. Now similar to our conversion of galvanometer into voltmeter, we are going to have our conversion of galvanometer into ammeter. So galvanometer can be converted into an ammeter. So here we have our circuit. So if you are going to see here, we are going to connect a shunt resistance in parallel with our galvanometer. So now here this is a battery. As we know, the positive of the battery is being connected to ammeter's positive and the negative of the battery is connected to our galvanometer, and the other end of the galvanometer here is going to the top terminal of my rheostat, and battery's negative is connected to the lower end of a rheostat. The other lower end is connected free, it is left free, it's called a free end. So across my galvanometer a shunt resistance is being connected. Okay, so if you could see now here, battery is positive, as we said, battery is positive is connected to my ammeter's positive. So the negative of my ammeter is connected to my galvanometer, and the other end of the galvanometer, as we said, is going to the top terminal of our rheostat. So from the galvanometer to the top terminal of the rheostat. So one end of the rheostat, you can see here, it is connected to the negative of the battery, and this end is being kept free. This is called the free end, so it is kept left free. And now across the galvanometer, this is called a shunt resistance. So shunt resistance is being connected in parallel to our galvanometer. Okay, so now if you could see, this is the circuit connection. First here we will see theoretically what is the S value I am getting, and then that is the resistance, and experimentally what is the value for shunt resistance I am getting, we will see. So here also the observation similar to our conversion of galvanometer to voltmeter, we are going to have our observations here. It is galvanometer's resistance as it is given behind the galvanometer, the values, G value, figure of merit of my galvanometer, K value, and number of divisions on either side of the galvanometer. We know already it is 30, and now the current that is required for producing the full scale deflection is going to be Ig equal to N into K. So that is N is 30, K is 20.4 into 10 power minus 6. So I am getting 612 into 10 power minus 6. Next, the range of my ammeter. So this is ammeter is here it is, everything is given in milliamps. So when you are going to convert it into ampere, so the range is going to be 30 into 10 power minus 3 ampere. So we have to convert it into ampere. So since the readings, everything it's all given in milliamps, so into 10 power minus 3 ampere we have to. Next is shunt resistance I have to find out. So this is what I have to find out. So S equal to IgG by I minus Ig is the formula for it. So Ig value I know already, G value also I know already, it has been provided in my galvanometer device only, divided by I minus Ig. I just have to substitute off these values and find out the answer. So when I find the answer, it is 2.063 ohm. So this is my theoretical value of shunt resistance. So S value, experimentally also if I am getting the same value or not, I have to check. Okay, so before going to that, shunt resistance length also theoretically I have to calculate. So this S value I am going to substitute it off in some other formula which is going to give me the length of my shunt resistance. So that is L equal to S pi R squared by rho. S into pi into R squared by rho. So S value I got it already. Pi is 3.14. R value for my galvanometer is given behind the device. So that squared divided by my resistivity value for the device also is provided. I am going to substitute that and find out the value, theoretically my L value. So this L value theoretically I have found out, and experimentally I am going to do the calculation and connection and check if what is the experimental length I am going to get. So I have got 32 centimeters already. So I am going to show how I got 32 centimeters. So here this is the crocodile clip of my shunt resistance. So I have to keep varying the length of my shunt resistance. So slowly I have to vary the length. So I can keep varying the length of my shunt resistance like this. So then at a particular point my galvanometer deflection will become 30, and here I will get 30 means amperes in my ammeter. So I am using a rheostat also for this adjustment. So let me check. I am going to vary the length of my shunt resistance. So almost it is coming to 30. So it should come to 30 and my galvanometer should show the deflection to be 30. So when I am means in this process, whatever is the length I am getting, I have to take that length. So this is the point at which my crocodile clip I am fixing it. So I have to remove it from my galvanometer, from my device, and measure the length. So I measured the length and it was found to be 32 centimeters. So it was 32 centimeters is my experimental L value. So this L value is very important, for which my galvanometer shows 30 deflection and my ammeter shows 30 milliamps. So now this value I am going to substitute it off in my expression S prime value. S prime equal to rho into L prime by pi R squared. So when I am substituting this value, experimental L value, I am getting the answer for S prime to be 2.27 ohms. So this is my shunt resistance value experimentally. So theoretical value of S already was found to be 2.063 ohms. So when I am comparing, they are going to be almost equal. So I can say we have converted our galvanometer into our ammeter. So by means how can we verify it? The L value and the S value, when you are going to check, the experimental value and the theoretical value are going to match with each other. Okay, this is our circuit. So thank you.